The constraints that we have on Constellation are, particularly with respect to the architecture, is all about mass and performance. How much mass can we deliver at what time, and the key there is performance, whether it's launch vehicle or propulsion systems. And with Copernicus, we're able to optimize our propulsion systems.
We haven't had a lot of lunar missions to design in the last 30 years, until now. So it's gratifying to me that we're able to still be very much a leader in the arena of interplanetary trajectory design. And Copernicus is a kind of tool that is exactly tailored for doing that.
The thing about Copernicus is that it's like a one-stop shopping. Everything is there for the user. It has a powerful engine. It includes optimizers, integrators. It's a modular setup. It has a user-friendly GUI interface, and it has a visualization capability on board so you can immediately see what the trajectory looks like if there's any issues. These are all brought together in one suite, and it makes one user very powerful. It also allows you to visually modify the trajectories, and that's very powerful for a single user, and it shortens the development time quite a bit. Copernicus is, by its nature, designed to be continuously evolving. However, it is a very mature tool as it is right now. It's gone through a tremendous amount of validation, and currently we use it in real line projects.
Well, one of the things that we always needed in a computer code was the ability to do precisely a variation of the specific impulse. And most computer codes for trajectories do not have that feature. That's one thing. But the other thing is that we wanted that variation to be optimal, to find an optimum solution. So those were the kinds of things that Copernicus enabled for us.
Copernicus, by design, is a generalized trajectory design and optimization system. And it can perform and analyze a whole range of missions, including sample return missions to the planets, asteroid rendezvous missions, asteroid orbiting missions. It can be used to design satellite tours around the exterior planets like Jupiter and Saturn. It can also host a wider range of propulsion systems and any number of spacecraft. The architecture by design accommodates all these possibilities.
We've used Copernicus on a number of projects. Currently we're using it in the Constellation program. We're using it to do a lot of the performance and mission analysis for the Orion vehicle, which is going to be the vehicle that takes the crew back and forth from Earth to the Moon.
The key role of Copernicus is to help us do mission design, to decide what the trajectories of the vehicles are and the propellant loads that we need to deliver the payload, the spacecraft, to various places around the Moon and onto the surface.
Middle of last year, we did a review called a Lunar Capability Concept Review, and we were reviewing where we stood in how much capability does the rocket have to have, how much capability does the lander have to have, and it's tools like Copernicus that were used to put that picture together and help us understand, you know, if I vary the crew size, if I vary how long the spacecraft stays in orbit around the Moon, how much propellant is inside the lander. You know, as I play with these different knobs, if you will, of the integrated problem, it's tools like Copernicus that give us an ability to go interrogate just how sensitive are those knobs. And so in that review that we had, the Lunar Capability Concept Review was wildly successful. Gave us our first real rich understanding of the integrated performance of this architecture.
For each launch date, we couldn't just go into a fixed orbit that we could use for multiple launch dates because we needed to have an impact that supported the viewing requirements and the lighting and the observation requirements that satisfied our science requirements. As a result, we had to design a variable orbit for each launch date Copernicus, we used that software to optimize the trajectory, minimize our delta V, and achieve a high impact angle of attack that we needed in order to maximize our science data return.
We use the program to do research. We also use the program to teach at the university and at outreach events at the public school system in Austin. I use it to teach basic courses in orbital mechanics. I use it to teach advanced courses in spacecraft trajectory optimization at the graduate level at the university.
Copernicus was a small project, kind of a lean, mean project, and we got what I think is an extremely powerful tool on a relatively small budget.
The intent is to be an evolutionary tool. It will evolve over time as the needs require it to be.
But it also has the ability to bring on board new techniques and algorithms that may be developed. For example, a controller or a guidance algorithm that's very specific to a particular vehicle. So those can be merged in just as an integrator, and an optimization capability would be. So we can very quickly tailor Copernicus to very specific vehicle needs if we want to, or keep it very general to do very general mission design and what-if kind of analysis.
And because of the architecture, we can accommodate a whole range of propulsion systems and any number of spacecraft, which make the tool very useful for the complex missions that are going to come online in the future. So we want to be there, we want to be there ready with a tool like this and make the necessary improvements and changes needed, for example, to solve problems we may have not even thought about.